start again. I will begin with a word of prayer. Dear Father, we thank you for this day, and we thank you so much for this opportunity we have just to talk about you openly. It's pretty help us to understand a little bit more about projective spaces today. In the name of our Lord Jesus, amen. So I'm a little low energy today, and it's time for me to get out of the race, so I don't know. Let's see here. What is that? It was not a happy boom boom. I do not like that. Ay, ay, ay. Please. All right. So, real projective space. We defined as the quotient by the group of homeomorphisms of Rn plus 1 with the origin removed. Which group was it? The group of dilations, right? So basically non-zero scalings. And so doing that makes lines through the origin not included, of course, equivalence classes of those are orbits of the group action. And so those become sort of the points in real projective space. And then we realized that there was a natural identification, let's say, correspondence between these real projective spaces and n spheres. And we noticed that we had this inclusion of the n sphere into Rn plus 1, and we had the inclusion, the unit vector map R of this into Sn, and so we get these natural mappings F and F inverse appearing from, the composition of the projection. So this is the antipodal projection, right? It maps, it projects pairs of antipodal points to one point in this quotient. So this is like pairs of x comma minus x and the n sphere. And then so there's natural mapping between those pairs of points, right, and projective n space. And it's pretty easy to see in the picture. It's like there's a mapping between this pair of points, right, thought of as one thing, and that purple line. That's the mapping. I mean, you can geometrically see it in this case. I think everything I'm doing here just as well works in the complex context. You can talk about complex projective spaces. Although, how does the sphere go? I guess we'll get to it. But any questions about this so far? About where we got to? We had mentioned that because we're quotienting, like this basically is a quotient by plus or minus the identity map, and so that's a finite group of the homeomorphisms of the n sphere, and consequently this is what? Hausdorff. And so if that's Hausdorff, this is Hausdorff, because F is a homeomorphism.
Is this related at all to the Riemann sphere?
I think so. It's a good question. What's the connection between this stuff and the Riemann sphere?
What is the Riemann sphere?
Yeah, that's a good question.
Sorry.
It's a totally legitimate question. So the Riemann sphere, you can think of it
I guess I should.
So here's like the complex plane, right? And then if you can imagine resting a sphere so that, where do we attach the bottom of the sphere? I'm trying to remember, probably the origin, right?
Well, I thought it was like sitting in the middle of the plane. Although I could be wrong.
I don't know. There's a couple different constructions I'm thinking of. Let's see if this one makes sense.
But it'd definitely be at the origin.
Yes, whatever we do, it involves the origin for sure. Anyway, so the mapping then is, so here's basically the thing is, the North Pole maps over here to infinity. You don't usually draw that. But on the other hand, you can draw lines. And so these lines, so a line from the North Pole to where it intersects the complex plane and we're viewing the complex plane essentially as like R2 inside R3, and this is actually something like, you know, this is usually I think you could just think of it as x squared plus y squared plus, you know, z minus 1 squared. I think you can use the unit sphere. You probably could do otherwise, but that's one way you could set up the thing. And so if you look at that particular point where it intersects the sphere, right, that point, let's say x, y, z, then that maps you to a specific point down here, which we might say is a plus ib.
Okay.
And so what this is called the stereographic projection. It will map the you know, Nathan, you might be right. I can't, golly, it's sad, but I don't. It's, especially today, I don't trust myself. Where's that stupid book? It's all right behind you. Now, look at the game one for a second here. Come on. Get out of there. All right. How's he set up? Come on. Oh, there it is. So, what's he do? He says the extended complex plane is the complex plane together with a point infinity. You can visualize the extended complex plane C star so that C star is C union infinity. One way to visualize the extended complex plane is through stereographic projection. This is a function or map from the unit sphere of three-dimensional Euclidean space to the extended complex plane. So he says any point other than the North Pole, we draw a straight line through the North Pole and P, and we define the stereographic projection of P to be the point X, Y. Yeah, I don't think I have it right yet. Yeah, you're right. He puts it on the plane. Oh, it survived. Curses. So I should have drawn something like this. What? No. I'm sorry, guys. Oh, I don't know what's wrong. I mean, he says that this is equal to x plus iy. So I think that's hard to see in my picture. Excuse me. And then. Sorry, I'm trying to see here where he puts the stupid sphere. That's the main question for me, right? He says the North Pole is 0, 0, 1. So it is this.
Right.
Yeah. Yeah, you're right. It is 0, 0, 1. Okay. So if this is 0, 0. So he's saying you draw. Oh, I'm sorry, he was introducing notation. So this point, that's inside. Oh man, see, I need a real chalkboard, this ain't making it. So this point, he used big X, big Y, big Z for, and then the point it maps to, he used little x, little y, little, he's being sneaky. That's the same x, okay. Because I was envisioning a projection down, which is definitely not the stereographic projection. It's not so simple as that. Anyway, let me just skip ahead here. You eventually get the following formulas. X is equal to x over 1 minus z, the big X, okay? And the y is equal to big Y over 1 minus z. That's a little bit of trigonometry and stuff to get there, but eventually you get that. And you can let's see here, you can also write it as like this: x is equal to 2x over the modulus of z squared plus 1, y equals 2y modulus of z squared plus 1. And z is equal to modulus of z squared minus 1 divided by modulus of z squared plus 1. So that would take you from this thing being basically, z x plus iy, right? So that's the reverse map. Essentially, this is how to go from the point on the complex plane back up to that.
Okay, I see it. So, because it's obviously 2 to 1 there, because you can use the lower sphere. It's 2 to 1 over there, right?
I don't think it's 2 to 1. I think so. Let's
You
see.
can't map it from like the bottom hemisphere to like another point.
Well, those points in the bottom hemisphere will map to the interior of the disk. That picture's not much good for anything. So like down here, so this would be like I think that would be the XYZ. I'm sorry, the x plus y, x plus iy. And then down here it would be the XYZ, right?
Oh, it's always mapping from the North Pole.
Yeah.
Okay, never mind.
Zip. Thank you.
I thought you could. Never mind. I for some reason was thinking you could map it from the North Pole, South Pole.
All right. So, I mean, you can study these formulas and see that too, right? Like, okay, so if big X is 0, and if big Y is 0, what is, that makes X and Y both 0, right? So that's actually, but if Z is also equal to 1, it's undefined, right? Check that out. If big X is 0, if big Y is 0, and if Z is 1, you have division by 0 in these. That is understood to be the one that maps off to infinity. On the other hand, in these formulas, if you have Z equals to what? To down here, minus 1, then you have 0 over 2, 0 over 2. And you see the south pole down here, all right, that is the one that's stereographically projected to the origin in the complex plane. Make sense?
Yeah.
And if you study these formulas, you can also see that the northern hemisphere of the sphere is mapped like outside the unit disk, whereas the southern hemisphere is inside the unit disk. The equator, let's say. And so the unit circle maps to the equator. Unit circle in the complex plane maps to the equator of the sphere. That's essentially those are essentially fixed points in this map. You can, let's see, any units. What would that be? A unit. If a unit circle in the complex plane has the equation modulus of z equals to 1, right? What happens if you have modulus of z? You have what? Modulus z equals to 1. 2 plus 1. 2 over 2. Y equals y. X equals x. You can see it. It's right there. So now I'm sure our picture is legit. Let's go back to Nathan's question now that we understand what on earth the Poincare... That is the Poincare sphere. The Poincare sphere is... No, Poincare sphere? Wait a minute, I want a Riemann sphere, right? Golly. Don't let me get away with that.
Wait, are they separate constructions?
There's more than one sphere to go around. There's, there are other things. Oh, come on. Well, he doesn't. What am I doing? I'm looking in Gamelin for the history of something. Well, that's just a fool's errand right there. Sorry. I should be looking at this. It's Vermeer. We are looking for, what was it? Stereographic projection, that much we know. The question is, whose sphere is it? $71. If you ever want to dig deeper into complex analysis, it is hard to beat this book. This is Reinhold Vermeer's masterpiece on complex analysis. Let's see here. Der Umstand, Klasse der Verstand müssen das Riemann es unterstanden hat. Blah, 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 blah. Several of Riemann's work were at first comprehensible only to a small readership. It is explained by the fact that the publication of general investigations of Riemann failed to illustrate his novel ideas thoroughly enough by carrying through the complete analysis of special examples. Comment by Schwartz in 1869. Well, that doesn't help us. Let's see here. Okay. I guess we could have Googled it by now.
Should you take complex analysis?
Yeah.
I just can't remember what I called it. Just name calling, right? You gonna put me out of my misery?
Yeah, I'm gonna try.
Okay, go for it. You're fine. I'm just rifling through my books.
Poincare sphere is something in optics, so I'm pretty sure it's the Riemann sphere.
Mm-hmm. Well, there's a... Okay. Right. Oh,
Yeah, it's the Riemann sphere.
definitely the Riemann sphere.
Yeah.
All right. Good, good, good.
Hmm.
It's funny. It's not
Half
even-
of these images have the sphere above the complex plane, and half of them have it cut in half.
Yeah. 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 Hmm. Hmm.
Hmm. As in projective geometry, the sphere can be thought of as the complex projective plane, P1C.
Riemann sphere. Riemann sphere. Definitely Riemann sphere. Yeah. But
Yeah.
you might find other.
Because when it's
You might,
above,
you might you might be able to find other models of the Riemann sphere. This is one model of the Riemann sphere. I think more sort of esoterically, you could say a Riemann sphere is a three-dimensional sphere which models the extended complex plane.
Yeah.
Certainly, there are other coordinatizations of that.
I like the cut in half better because obviously when you have anything below, like in the southern hemisphere,
Yeah.
you know it's inside the unit disk.
Yeah, the formulas here are pretty nice.
Yeah.
But I have seen the other in something I was doing, and I'm sure there's some convenience. Okay, anyway, I digress. Okay, so what was the... What did you say, Nathan?
Oh, as the
project-
Wikipedia article says that the sphere can be thought of as the complex projective line, P1C. But I don't understand how it could be if here it's a 1-to-1 mapping to the plane.
Yeah,
But-
that one's a 2-to-1.
So
Yeah,
what would the,
I mean, so maybe they're
what
just
would the-
homeomorphic.
Well, what would the complex... You know, what is CP1? Right? Is that the...
Or
would-
P1C.
I guess for us we would do, yeah. I would assume that that's equal to C2 without the origin. Aw, man. Not as awesome as it was last time.
Oh, I
Right.
see.
Mod what? The dilations, right? It may just be this chalk, actually, that's the problem. But, so, it's, So I don't know what can I say about that. So you said that was, you could identify that with the Poincare. I mean, this was, you could think of this as the Poincare sphere.
Riemann sphere.
Riemann sphere. I'm an idiot. Riemann sphere. Which of course is the same thing as the extended complex plane, right?
Yeah.
Oh, it kind of makes sense in some sense because, like, what is the real projective plane? You know, think about that for a second. Well, the real projective plane is what? It's R2, right? And then you say everything through the origin along a line is the same point, right? And then so there's obviously an identification of that with the circle, right? But we should remember, and maybe we don't remember this. Maybe we haven't even talked about this, I don't know. But of course, the circle is what? S1 is what? S1 is nothing more topologically than R union with infinity. If you think about the one-point compactification of the line, take the line, right? Tack on infinity. Circle. So the one-point compactification of the line is S1.
Right, so even though our particular construction of it, it's a 2-to-1 mapping, and here it's a 1-to-1 mapping, there's still
Which is
homeomorphic.
which is the 2-to-1 and 1-to-1? What are you speaking of 2-to-1?
I'm saying our construction here, there's 1-to-1 mapping between the complex plane and the points on the sphere.
Uh-huh.
Whereas here, our lines to the origin, it hits 2 points on the sphere.
Ah, right. Yeah. However, where is C2 in that picture?
R3?
C2 is 4-dimensional.
Oh, yeah.
Yeah. So best I can do here is by analogy or by the same mathematics. I mean, personally, I can't visualize C2.
So, I mean, never mind. It'd be a 4 to never mind, that wouldn't be useful at all anyway. I just wanted to say it's a 4 to
But I think essentially these same arguments we go through here, at least set up P, PNC. Well, let's just one. Where was I? Here, let me foolishly try to erase these. Yeah, see, I definitely need a real chalkboard. I mean, this is not bad. It's better than no chalkboard, but I think I need... You guys agree, right? I need a chalkboard, right?
You tell Jenny your students think you do too.
Alright, well, anyway.
That's the real reason you're having a pizza party. We're going to come over and...
It's my wife that I need to spend $300.
So I need to
spend $300 to $500 on a chalkboard, yes. So sure she'll be very happy to listen to your arguments. Okay, so let's look at this example here. I better erase some of this stuff, I'm sorry. Whatever. Where did I put the juice? Oh, thank you. All right, so example 5.20. Let's see if we can understand this one. He says, consider the space X, which is the disk D2, mod some equivalence. What is the equivalence he's going to use? Oh, it's literally the... So two-dimensional disk, So D2 is, you know, x in R2 such that the norm of x is less than or equal to 1. And the equivalence he wants to consider is the one that identifies antipodal points on the boundary. So I'll try to illustrate that for you guys. Come on, can't use stupid marker. I mean, you kind of know, right? So like this point and this point, right? You have those x are equivalent, right? And then of course you also have that x is equivalent to x for x within the disk. I mean, every point is self-equivalent inside the disk, but then the points on the boundary are. You can kind of like, I think, is that I feel like that's the sphere, is it? I mean,
Yeah,
Is it,
that makes
or-
sense. Well,
you're like.
wouldn't you have to identify everything on the edge as one point and make it a sphere?
But that's my other, yeah, right. So maybe it's not the sphere, but it's like you're gluing points on the edge together. You're right. If I made all the boundary 1 point, then it seems like it would be intuitively a sphere. All right. So the adventure continues. So so mathematically, he's like x is equivalent to y. What? X equivalent to y. If and only if what? If and only if x is equal to y, or absolute value of x equals to absolute value of y equals to 1, and x is equal to minus y. Okay, those are them's your choices. All right. He said the aim is to show that x is homeomorphic to the real projective plane. Okay, so good. It's not the sphere. For starters, he says identify the disk D2 with the upper hemisphere. He's like, well, it's basically like, okay, so you can take the disk, right? And you can identify it with the upper hemisphere, right? Where s plus 2 is what? X, Y, Z. Such that x squared plus y squared plus z squared equals 1, and z is greater than or equal to 0. All right. Now here's a mapping I understand. The homeomorphism between the disk and that upper hemisphere. I think you guys can tell me what the homeomorphism is, right? I mean, it's not. You take the point x, y, z and map it to what?
The point directly below it.
Exactly, yeah. So we have that mapping, let's call it, give it a name on the psi of xyz equal to xy, where we're of course viewing D, we're identifying D with D cross 0, fine. This is a homeomorphism. What's the inverse?
Root x squared plus y squared?
Almost.
Oh, yeah.
You got me. You suckered me into that plus. You talked me into that. I blame you, Nathan. You see here. Talk me into that plus. I think. It's not even your fault. All right. Then what? He says x is What is x? X was the thing we started with. He says x is homeomorphic to S2 mod the antipodal identification you guys follow this? X is homeomorphic to S2 plus mod the antipodal identification. So he says we take S plus 2 mod the antipodal equivalence of the sphere. It's kind of boring for most of the points on the sphere except for the, So what's that do? I see what's going on. I mean, it's, right, do you see it? So it's like, it's saying these points are equivalent, right? Like, if these points are minuses one of another. And if you look at, that's the same equivalence as the one up here, right? Try to make that more precise with this. X is homeomorphic to, so it says Sx rather, is homeomorphic to this. I think he's about to prove that. So he says let I, look at I as the inclusion of the upper hemisphere into the sphere, right? You guys know what that map is, right? That's just the mapping xyz goes to xyz for every xyz in the upper half sphere. And then what? The projection looks at the projection map from where? From S2 to the projective 2 space, real projective 2 space. And then he says P is what? P is going from S2 plus to X is, what is this? He says this is the canonical, what? The canonical quotients, he says. Yeah, the following, this diagram will be helpful, I think. Here's the diagram. We have S2 plus, that includes into S2 under the inclusion map I. S2 projects down to P2R. All right. We know, remember, we remember that. We take the pairs of antipodal points and they project to the projective lines. Remember that map? That's this map. I think. Wait a minute. Oh, yeah. And then this one, we have P, and down here we got X. This guy, he calls J. Where's J coming from? I understand the map I think I understand the map. I understand the map P. I think P is what I called psi, right? Right. Just the projection map. He called it P. I called it psi. Whatever. What can you guys say about J?
Equivalent to pi of I.
Pi.
Oh, no, sorry, never mind. Would be.
I do have an inverse.
I of inverse of.
Yeah, I do have an inverse of this. I mean, I could work with that, I suppose, right?
Yeah.
So.
Pi of I of phi inverse.
Pi composed with I composed with psi inverse is equal to J. It's okay. Pitchfork. Does that make sense? So psi inverse goes to here, I goes to there, and then pi finishes the job. He claims, right, what does he claim about this J map? He says that we have a commutative diagram of continuous maps, and our J is bijective, and maps a compact space to a Hausdorff space, so J is a homeomorphism. Let's see here. All right, so the fact that X is compact, I think, is somewhat clear because, remember the quotient of a compact space is compact. So X is formed by a quotient of D2, which is compact, so X is compact. And
panicking because you won't know where I am. All right.
Oh, we figured out P2 was Hausdorff last time, remember? This was that. Uh-oh. A certain professor has found us. Behold, you're on tape. But
That's your blackboard.
that's my blackboard.
It's actually black.
Yeah, more or less.
Green.
No, you want to. That's the problem.
Yeah,
Yeah, it's not quite right. I was telling them I need a real chalkboard, but
yeah.
hopefully they will come over and convince Ginny of it.
You know, I wonder if there's any in